Hello everyone. Let me continue the discussion of drawing what is called as shear force diagram and bending moment diagram. I want to save time. I shall not go in telling you what is shear force, what is bending moment, what is that diagram, etc. I have spent all that in my lecture. I have chosen a very simple problem, again a cantilever. Okay, so not much change. So in the earlier I had two loads and I have only one load now. And say the load is say P is the load and it is acting not at the free end and it is acting somewhere in between, and say this distance is 0.4 L and say this is 0.6 L. I have made it a general one, I have not taken any numerical value this time, and as per the procedure whatever I have told you, and since this is a cantilever, and choose the free end as the reference. So this end what we are going to choose, this is my reference. This is the reference, okay? So once you take the reference, then identify the sections, identify the portions of the beam where you want to take section. Okay? So the first step I shall choose. So B is my reference. P is reference. So this is the first thing what I have observed. Then what is the next thing? The portion. So portions what I have identified for taking section are portions BA and AO. So I have called it as O and this is A, this is B. You can name in a different way also, it doesn't matter. Portions BA and AO. Okay, the next one, what is to be done? Portion BA. Let me go for portion BA. Without wasting much time, I shall straight away take it. Between B and A, I want to take section. Say something here, I would like to cut it, and I draw what is called as the free body diagram. So this end I know that it is B, and please remember this is not A. This is where I have taken section, and where is that section? The section is at a distance x from the reference. And so how long this x is valid, whatever this diagram, and any other load, and no other load. Please remember P is acting at A, I have not reached yet A, and therefore in this portion I don't have any external load. And imagine the positive shear force. The positive shear force, as you know that, so the beam portion what you are considering for analysis is to the right side, and therefore it is upward shear force is positive. Let me call this as Bx. The upward is positive, and similarly this is the bending moment which I am taking it as positive Mx. Okay, so you can go back and check what sign convention you have followed. Okay, and I would like to be consistent with that, and that's what I would like to follow. By chance, if your sign convention is different, no problem. But don't change it for portion to portion. For one entire problem, whatever you want to have sign convention, you take it, no problem, nothing will happen. But you cannot take one sign convention for this portion and another sign convention for this portion. In that case, you will end up with the wrong results. Okay, so no problem. So now I do not have any external load here in this portion. I don't have any external load. As I said, I shall write down what is the x range. X is the 0, the smallest value. When x is 0, I am at B. And the largest value is 0.6 L. So x, this length is L, and this is 0.6 times that, and this is 0.4 times that. Okay, so now you find out what is Vx. Vx, you start with Vx, apply the equilibrium conditions Vx, and I don't have anything else. So Vx P is equal to 0, and same thing is true with Mx equal to 0. That means the portion BA, as it is not having any bending moment, the bending shear force is 0. That means 0 is the shear force throughout this length. This is what is the line. As we know that this shear force B is equal to 0, this line, and B is positive this side, and V is negative this side. Similarly, N is 0 here, and this side is positive, and this side is negative. On the same lines. The bending moment is also there. Therefore, I draw what is called as throughout the length this BA portion, the bending moment is 0. So then what is called as portion? What is the next one? Portion AO, from A to O. Okay, take a section between A and O. Okay, this is what I would like to draw. I am taking the right hand side portion. This here is B, and probably this is my end A, and this is where I have taken section. This is my reference, and therefore the section is at a distance x, and therefore any other load? Yes, I have one load here at point A. This is equal to P kilonewton. Okay, what is this distance? Just for you may require later on, just write it down. So from here to here is x, and this distance, as you know that it is 0.6 here, and therefore this distance is x minus 0.6 times here. Yes, minus 0.6 times here, this distance. Okay, so now show the positive shear force. Again, this is the section. The beam, what I am considering is to the right side, and therefore my positive shear force is this way. And my positive bending moment is this way, mx, px and mx. Okay, apply the equal. And before that, you write down what is the range of x. What is the smallest value of x? That is nothing but 0.6 times here. Please remember, this is your reference. This is where your section is here, and the section you want it always between A and O. It should not come to the right of A, or it should not cross O. And therefore, what is the smallest? That is, it can come up here. What is the value of x? It is 0.6 here. And what is the largest value of x? That is nothing but here. So therefore, now apply the equilibrium conditions. Very simple. X, we have started this. This is your shear force, positive shear force. This is moment. Okay, come. This is the force which is in the downward direction, minus P. And any other force beyond that to go up to your reference. Okay, you don't have anything. This is equal to 0 because it has to be remain in equilibrium state. Therefore, Px is equal to P. So there is no x on the right hand side. There is no x on the right hand side. Therefore, the shear force throughout the length AO, it remains as P. Therefore, you can draw it. So what is the shear force at A? It is equal to P. So I have to draw for shear force. This is bending moment diagram. The shear force. So here is P. And what is the shear force here? Here also is P. Because I am talking about the portion A and O. So therefore, this is what is the shear force diagram. So here it is 0, and this is the value of P, and this diagram is called as SFD, the shear force diagram. Okay, so similarly, let me calculate what is mx. Okay, let me do it here. Mx, I start with this mx. I am taking moment about this section. This Vx is in this force in the same section, therefore it will not form any moment. Then P will form moment about this section. What is the kind of what is the sign sense the direction, that is clockwise, and my mx also is positive clockwise, and therefore this is plus. This is equal to P multiplied by the distance between the force and the section. This is equal to x minus 0.6 L. Okay, so then no other force, nothing, that's all. This is equal to 0. Therefore, mx is equal to P multiplied by x minus 0.6 L. Okay, so note what is the mistake? I take it to the right hand side, I have a minus sign. The minus sign. So therefore, so observe this carefully. So check, I have x on the right hand side. So what is the first observation? The bending moment is going to vary. It is not constant. Okay. So bending moment is varying. It is not throughout between A and O. It is not same. It is varying. That is the first observation. Okay. Then check what is the power of x. The power of x is, I have only one term x and x raised to 1. That means it is a linear. That means it is straight line. The variation is straight line. Okay, I'll write that. The variation of mx is a straight line. Please write that. I am skipping it. So when you know that you are going to draw a straight line, then identify the 2 points. I mean, find out the bending moment at 2 points. Then join them. That is the line what you intend to draw. So how can I get it? I shall get a bending moment. What is it at A? How much is the bending moment at point A? Okay, for point A or the section at point A, what is the value of x? What is the value of x? X is 0.6L. So substitute 0.6L minus 0.6L, it becomes 0, and the bending moment at point A is equal to 0. Then similarly, what is the bending moment at point O or at section O? So imagine the section at O. Okay, what is that is nothing but the largest. So L, so x is equal to L, that is nothing but minus P into L minus 0.6L. So L minus 0.6L is 0.4 times L. This is nothing but minus 0.4 into P into L. What is the unit? What is the unit of P? In general, usually is kilonewton. And L is in meters. Say kilonewton meter. Minus 0.4 PL. Can we quickly draw it? So what is the bending moment at A? I know that it is 0. And what is the bending moment at O? It is minus, therefore it has to be drawn downwards. And how much? Draw a line and write what is the value? 0.4 P into L. And how is the variation in between? The variation is a straight line. So this is what the bending moment diagram for this point. So I hope you have understood. So slowly, gradually I am increasing the complexity. I don't think this problem is difficult than the previous one. Maybe a practice problem I have taken it. Okay, now I shall change a different load. Okay, I would like to change the load. Not only point load, I shall have something else. Maybe a moment, or maybe uniformly distributed load, something like that. Okay, I shall have it. Okay, again, let me discuss the various loads of the cantilever and then I shall move on to simply supported beam. Doesn't matter. Okay, this is a cantilever and this is of length here, and say this is O. Okay, then I am applying a load. Okay. This is the moment, and this is m naught K kilonewton meter. This is known to me, and the length of this is say L. L is the length. So this is all I know. Okay. So now for this, draw the bending moment diagram and shear force diagram. Okay. Let me name this. Say this O I have made, and let me call this again. What is this? This is a cantilever which is subjected to what? Subjected to a moment. Moment m naught kilonewton meter at the free end. It may be applied anywhere else also. Please remember, I have a problem where it has been applied at the free end. Okay, make preparations. That means I shall draw it like this. Since I don't have any load in between, and therefore there is no need to draw it. Then identify the portion. As I have one load at the free end and I don't have any load here, the portion is OA. So what is the reference? A is the reference. That is the first observation what you do. Because for cantilever, always choose free end as the reference. Okay, that I do. Then, so how many portions? Only one portion. AO, only one portion. AO is the portion. Then go for portion AO. So in one stroke you will be able to complete the diagram. Okay, what is the next step? Take a section between A and O. Take a section between A and O. So somewhere here, you take it. Draw free body diagram. Okay, With this end is what is your A. And this is my reference, I know. This is the section where I have taken it, I have cut it. And where is it? This is at a distance x from the reference. Show the external load. I have a moment here and it is clockwise in direction and its value is m0 kilonewton meter. Okay, then show at the section, again the portion of the beam is to the right hand side and therefore this is my positive shear force. I assume that the shear force there is positive. Okay, so I shall assume, and my assumption if it is wrong, I may end up it as negative. So that value will be negative. Similarly, the bending moment will be in this direction. This I call it as m suffix x. Please, I hope you understand m suffix x. The bending moment at the section where that section is at a distance x. So that is why I am using mx, vx. I hope you understand. Mx, Vx in general, I assume that they are varying with respect to x. Okay, so now all that things have been shown. Now apply the equilibrium condition. Start with Vx, the force, yes, Vx upwards. So come here. Any other force? Yes, I don't have any force. This is moment. Please remember, m0 is a moment, and therefore it is not going to come in this. Vx is equal to 0. That means the shear force in the portion AO is 0. I didn't make it that equation. So this is the shear force, V is equal to 0. And this is the portion. To draw bending moment, I shall assume that M is equal to 0. So what I have got? The shear force in the entire portion A and O is 0. Therefore, the shear force diagram is like this. This is your shear force diagram. Okay, so now let me go for what is called as mx. Mx, okay, this is clockwise and I have written clockwise as positive because I am writing this mx as positive. It may be whatever the direction, and go back here, check what is the direction, what is your positive direction of m. So clockwise is positive. Okay, fine. Then this Vx will not produce any moment, then you have one more moment m0. So m0 is also clockwise. Therefore, it is plus. Plus what? Plus m0 is equal to how much? This is equal to 0. Because sum of all the moments also must be 0. That is part of the equilibrium condition. Okay, so get the expression for mx. Mx is what? Mx is minus m0. And I don't have again what is the x on the right hand side. What is your first observation? The bending moment in the section, in the portion A and O is constant because it doesn't have on the right hand side, you don't have x term. Okay, so it is constant. When it is constant, there is no question of variation, etc. etc. Okay, then you can easily draw it. So what is the bending moment? At the entire portion is constant. How much? It is minus m0. Okay, what is the bending moment at the free end? So how much is this value? This is m0. It is negative. What is the bending moment at the fixed end? It is m0. Negative. And how does it vary? It is a constant. It is not varying. It is same throughout. This is what is bending moment. This is called as bending moment diagram. I hope it's clear. Okay, let me take one more. So I shall slightly change it now. I shall have one more load, different. I am taking only one type of load at a time. Okay, so let me be familiar and then I shall go on mixing all these types of loads. Maybe I shall have something like this. I hope you can remember it. What is this? This is uniformly distributed load. This is called as uniformly distributed load. And how much is this load? This is a value W. W may be 10, 15, 20, 5, anything like that. W. W what? What is the unit of this? It is so many kilonewton. W kilonewton per meter. Per meter. So what is the length of my beam? It is a cantilever. It is so many L meters. Okay, this is O and this is what I shall call it as A. Okay, so observe, quickly go through the given problem beam. So check what is the type of beam, the cantilever beam. What type of load it is subjected to? It is subjected to uniformly distributed load. I hope you understand. The load is not a point load. The load is not acting only at point. It is spread over the entire length. So at every point, you have a load equal to W kilonewton. W kilonewton, W kilonewton, W kilonewton, W kilonewton, W kilonewton. Throughout this length, you have what is called as W kilonewton. If I want to know, only for my curiosity, what is the equivalent point load? So I have W kilonewton at one point. So how many points do I have, or not points? What is the length of that? Length is L meters. W kilonewton per meter multiplied by L meters. So meter cancels. W into L is the load. That is called as equivalent point load. Okay, anyway, that probably would have been required if you are trying to find out what is called as the reactions. So here, right now, it is a cantilever. For cantilever, you need not find out the reactions. Then after, with that condition, you also have one more condition. In that case, choose the free end of the cantilever as your reference. Okay, so therefore, A is my reference. That has been automatically chosen. Okay, what is the portion now? So since from here to here you have only one type of load, and therefore portion is one portion. You have only one portion, AO, only one portion. Okay, make ready here. Okay, I shall have this V equal to 0, and I shall also have what for us M equal to 0. So it is understood, positive upwards, negative downwards, like that here also. Okay, portion AO, then this is what? Only one portion, therefore I can straight to underline that itself. Then what is to be done? Take a section between A and O. Take a section between A and O and draw the free body diagram. Okay, draw it. Fine. So this is my A. So this is not O. This is the section where I have taken. And where is it? This is at a distance. This is my reference. This is at a distance x. And what type of load I have? I have called as this is W kilonewton per meter. This is the load I have. Okay, this is where I have taken section. Therefore, I have here shear force. This shear force is my positive shear force according to my sign convention, and this is my bending moment called as Mx. Okay, so now I have to apply what is called as the equilibrium condition. Okay, let me start with say Vx. Vx is the upward force which is positive. Then I have this load. Please remember this load. What is the direction of this load? This load is in the downward direction. So my upward force is positive, therefore downward force is negative, the minus. So first decide plus or minus. Then think of what is the magnitude. Okay, how much is the magnitude? What is the equivalent total downward force which is acting in the downward direction? So I know that it is W, and this is spread over a length x meters. What is the total downward load? That is this W multiplied by length. So Vx minus W into x. So any other load here? This entire portion load has been taken. It is not just point load. I don't have here. Okay, the entire load has been taken, and this is no other load. This is equal to 0. So therefore, what is the expression for Vx equal to W into x. So please remember, what will be the unit of this? This will be so many kilonewton. W is so many kilonewton per meter multiplied by x. And one more thing, I forgot to write it down. I shall go back and complete that. What is the range of x? What is the smallest value of x? It is 0. And what is the largest value of x? This is here. Write this image. So normally I keep writing it. The moment I write portion AO, what is my x here? I normally write. Okay, no problem. Okay, come back here. Shear force. I know that. Okay, observe. So is it constant? It is not constant because I have x here. So it is varying. It's the first observation. Shear force varies. Okay, how does it vary? So I have only what is the power of x? X raised to 1 only. So therefore, do you agree that shear force varies linearly? Shear force varies according to a straight line. Straight line variation of shear force. Please write down that. Straight line variation of the shear force. So you want to draw shear force, that is straight line. Okay, get 2 points. One is the shear force at point A. The other one is shear force at point O. So for A, what is the value of x? For A, that means if you take a section at A, what is the value of x? This itself is your reference. You are taking section there only. What is the value of x? X will be 0 and substitute x equal to 0 here. So shear force at point A equal to 0. And similarly, so if you want to take section at O, what is the value of x? X is equal to L. So therefore, this is WL. Okay, completed. So what is shear force at point A? It is 0. So at point O, how much it is? It is W into L. Is it positive or negative? It is positive. So how much it is? This is W into L. So how does it vary in between? So you are written here straight line variation. Therefore, this is straight line. Okay. So later on you come to know sometimes it will be a curve. Okay. Since we have not come across any such problem, probably you will not appreciate either constant or straight line variation what we have got so far. Okay. Probably this also you may meet. Okay, this is the shear force. Now let me complete the bending moment. Let me go for bending moment. So let me quickly write down mx, positive clockwise. Okay. So now, how to calculate the bending moment because of this uniformly distributed load. So for that purpose, only for calculation of bending moment purpose, I shall redo it. So A. And this is where it is my section. This is my mx. Okay, and this is where I have dx. I don't want to have UDL. And what is the equivalent point load I would like to take whenever I write down the moment equation? So how much is the point load? I know that it is W into x. W multiplied by the length x. So where it will be acting? It will be acting at the center of gravity of that portion of the load. What is the center of gravity? That is nothing but it is uniform load. And what is the center of gravity of this portion? It is the midpoint, and therefore it is here. So I know that from here to here is x. And what will be this distance? X by 2. And what will be this distance? This is x by 2. So W into x will be acting at the midpoint of that portion. Okay, now come back here. So to write this such diagram, you either draw it mentally or you draw it at some rough place. Okay, rough place. Maybe initially you can draw it. After doing some problems, probably you can do it mentally also. Okay, mx, dx will not produce any more moment. Then this W into x about this, that also is positive, therefore it is plus. So W into x is the force. Please remember, it is not moment. This is the force multiplied by what is the distance? X by 2. X by 2 is the distance. So this is equal to 0. Well, you don't have any other moment. Therefore, mx is equal to minus, first of all, W x into x by 2, that is x square divided by 2, minus w x square by 2. This is the bending moment. Okay, so bending moment between A and O, is it constant? No, because I have x. So it is varying. So is it straight line variation? go back to the coefficient of x, the power of x, not coefficient, power of x, x raised to 2. That means it is not straight line variation, it is a curve. It is a curve. Okay, when it is a curve, then at least 3 points are required. Okay, to draw a smooth curve, at least, not just 2 points will not be sufficient. Okay, if you get only one at here and the other one here, you don't know, there are so many. Let me try with only 2 points first of all and convince you that at least 3 points are required. Okay, so bending moment, okay, let me get at point A, bending moment at A. What is the value of x? X is 0, bending moment is 0. So bending moment at O, bending moment at O. So O at O, x is L. This is minus W into L square divided by 2. Okay, let me try. Okay, so this I know it is 0 and it is negative, and therefore I know this value. So how much? This is W L square divided by 2. So how does it work? It is definitely not straight line. It is not straight line. Okay, if it is a straight line, it would have been like this. It is not straight line. Then what are the different possibilities of the curve? So let me draw it here, straight line. The curve may be like this. Maybe, I don't know. Or the curve may be like this also. I know that it is not straight line. If it is straight line, it would have been like this. Okay, the curve, I know that it is a curve. Whether is it of this shape or is it of this shape, so that I don't know. Therefore, to decide that, what I do, I shall take down, I shall find out what is the bending moment at one more point, say here at the midpoint. At this point, I would like to find it. So, how much is this? This distance, since I know that this is L and this distance is L by 2. So let me call this as, say, point B. So I shall find out one more point, the bending moment at B. So what is B? B is at a distance L by 2. So let me substitute here, minus W by 2 as it is. Okay, what is X? X is L by 2. Whole square. Okay, so this is equal to minus W into L square. Okay, this 2 raised to 2, that is 4. 4 into 2, this is 8. Minus WL square by 8. Okay, at the point B, the bending moment is WL square by 8. So this is WL square by 2, and the bending moment here is 1/4 of this, 1/4 of this, a very small value. So how much is this? WL square by 8. So what is the shape of the curve? Whether it is like this or like this, you have got it now. So you start here, such that you start from here and it has to touch here and it has to reach here. Draw a smooth curve. It has to be like this. This is what we call it as the bending moment diagram for this. Please write down what is the value here. This is WL square divided by 8. I hope you understand. Okay, so maybe when we meet next time and we shall have combined all these loads in one problem and then solve cantilever and say bye to that, then we shall move on to what is called as a simply supported beam. All the best, please keep practicing, that is very important for this.